Hello and welcome to our discussion about least squares regression. So we're going to be talking about ways to model behavior based on data points and then with prediction. So we're going to interpret a regression line. We're going to talk about prediction. We're going to talk about residuals in the least squares regression line. We're going to talk about calculating the equation of a least squares line, how well the line fits the data based on residual plots, and then R squared in regression. And then we're going to interpret some computer regression output so you know where to find the slope and the y-intercept in the data or in the output. And then we're going to talk about correlation and regression. All right, so this is a regression line. The regression line is a line that describes how a response variable y changes as an explanatory variable x changes. So we use this line to predict the values of y for a given value of x. And this line here is a look at a regression line that relates fat gain to a change in non-exercise activity by individuals. So researchers took a look at individuals' consumption and then their exercise activity after a given starting point. And if it increased, they took a look at relatively how much fat gain occurred without any additional activity. So you can see that there are some data points where non-exercise activity decreased, but please notice that this value here would be where the y-axis would go. So the y-intercept is going to be right around this area. All right, so the regression line is describing a relationship between x and y to make predictive estimates based on changes to the x variable. All right, so here's a regression line equation where y with this hat on it is the predicted value for y given some value of x, b is the slope, and a is the y-intercept. So x is the explanatory variable, and then y is the response variable. All right, so the regression line that was generated was 3.505 minus 0.00344 NEA, which is non-exercise activity in calories. So as the non-exercise activity went up, the amount of fat gain generally went down. And so here's a line that establishes that relationship. All right, so we can use this equation for the regression line to predict the amount of fat gain burned through non-exercise activity. So the question is, if we burn 600 NEA calories, what is your expected fat gain? And so we're going to multiply the slope value by 600, and we're going to determine that the fat gain is going to be 1.441. Now this fat gain, you're going to have some fat gain regardless, unless you go past a certain number of fidgeting calories burned. And so let's say we take 6,000, not 600 NEA calories, then what's our expected fat gain? So if that's the case, we end up losing weight. So the formula here is 3.505 minus 0.00344 times non-exercise activity in calories. And so you can see the effect on increasing the x value in terms of fat gain. And this is, again, a predictive model. So we're extrapolating based on the equation and the regression line to predict the amount of fat gain given the amount of calories burned through non-exercise activity outside of the domain of provided points. So we don't have a value for something greater than 1,000. And sometimes we don't have specific values or data points, but we can use a line to predict where the fat gain value will be, or where the y value will be given the regression line. All right, so then let's talk about residuals in the least squares regression line, and then calculating the equation of the least squares line. So there's going to be some work in doing that. All right, so what's a residual? A residual is the difference between the observed value and the predicted value. So if I have some data point as my observed value here, and my predicted value would be the value that you would get using the equation for the regression line, so the data point on the line. And then in this case I have a positive residual, in this case I have a negative residual. So here's a data point, subtracting the predicted value gives us some residual increment, and this is only measuring the difference in the y value. So predicted output versus the actual, that's going to be your residual. All right, so the least squares regression line is the line that makes the sum of the squared residuals, right? So we square all these residual values and we come up with a sum. And the idea is to minimize that sum. And so the least squares regression line minimizes the sum of the squared residuals. All right, so this is a line that minimizes the area of these squared residuals, or the area of the boxes. Right, so there's some calculated work to be done. I'm just going to highlight this in least squares regression line. And I'm not going to go through it in its entirety. Okay, so now we need to calculate the equation of the least squares regression line. Of course, you can do this in your calculator, but I want you to be able to do this by hand. So our goal is to find this line. Predicted value is equal to y-intercept plus slope times the explanatory variable. All right, so we need to figure out b and a. So in order to figure out b, we need the correlation value, standard deviation for y, and the standard deviation for x. So the b value is equal to correlation times the standard deviation for y over the standard deviation for x. And then once we have this b value, we're going to use the mean values and the b value to calculate the a value. All right. So let's go through this step by step. We're going to find the mean for x and y. Then we're going to find our standard deviation, sample standard deviation for x and for y. Then we're going to use our standard deviations to find b. And then we're going to use b and the mean for x and y to find a. All right, so that's how we're going to do it. So let's go through an example so you can see this done. And then you're going to do one. All right, so here's my fat gain, NEA change, and fat gain. So the first thing I want to do is calculate the mean for x and y. So I have my NEA change. That's going to be x, and fat gain is going to be the response variable. So I'm going to calculate these means. So I get the mean for NEA change at 324.8, and for y, the fat gain at 2.388. All right, so now I'm going to calculate our standard deviation for y and x, and I get these values for our standard deviation for y and standard deviation for x. And now I'm going to use that to calculate b. So b is equal to the correlation coefficient times standard deviation of y over the standard deviation of x. So I substitute these values in, and now I have my b value. So negative 0.00344 kilograms per calorie. All right, so now I want to use this value for b to solve for a. So I'm going to go back and I'm going to get the values for the mean, 2.388 and 324.8. So 2.388, so this is the y, the mean for y is equal to a plus the b value times the mean for x. So we're using, in order to find the y-intercept, we're using the fact that least squares line passes through the mean value for x and the mean value for y. Okay, so now we're going to calculate this value for a. We end up with 3.505 kilograms, right? So we're just solving for a in this case, multiplying this out, and then subtracting it from 2.388, and we end up with 3.505. If I got this right. Yeah, so we're going to add this back in, so that's right. Right, so we end up with the regression line of y is equal to 3.505 plus b times x. Right, so that's how it's done. Right, so let's bring this to our classwork 3.2.1. All right, so the number of miles in thousands for 11 used Hondas has a mean of 50.5 thousand miles and a standard deviation of 19.3 thousand miles. The advertised prices have a mean of $14,425 and a standard deviation of $1,899. The value for R is negative 0.874. So I want you to use this information to find the equation of least squares regression line by hand and explain what type of price change is expected for each additional 19.3 thousand miles. Okay, so before I move on, I just want to, so please copy this down. I believe this is your only classwork problem, by the way. We'll have more in-class work to do. All right, so let's talk about standardizing variables, and we'll go through this more. Converts the mean to 0 and the standard deviation to 1. So more on this later, but when we standardize, then the mean is 0. And the standard deviation is 1. Okay. All right. So just wanted to highlight that. All right. So let's talk about how well the line fits the data, residual plots, how well the line fits the data for R squared, and then we'll wrap this up. Okay. So a residual plot is a scatter plot of the residuals against the explanatory variables. Residual plots help to assess how well our regression line fits the data. So if we see points that are way above and way below the line, right, then we know that the regression line is going to have some error in its predictive value. The closer we can get with these dots, and the smaller the standard deviation is for this regression line, then the better it's going to adhere to the line, and the more accurate our prediction is going to be. So essentially what we've done is we've just rotated this line to make it a horizontal line, and then we've taken a look at now the predicted line and the actual values. So the residual plot should show no obvious pattern, so it should be kind of like a scatter plot a little bit. But we should not have points that are very far from the line. If that's the case, then we have a concern about the predictive nature of the regression line, and also we're going to have to make accommodations for the deviation, the possible error in the line based on how far those data points are from the line. All right, so standard deviation of residuals, which is what we're starting to talk about, is a mean prediction error of residuals. Standard deviation tells us how far predictions are on average. The mean prediction error of residuals is 0, right? Because what we're trying to do is we've zeroed out this spread here, the plus and minus of the residuals. So if we were to take the mean value, we'd end up with 0. But the standard deviation is going to tell us what the spread is generally for each data point. Okay, so it's going to tell us how far off our predictions are on average. The greater the standard deviation, then the less sure we're going to be about a given predictive value, and also we're going to have to make accommodations for that predictive value. Okay, so the standard deviation of residuals is calculated by taking that y value for each plot, subtracting it from the predicted value, right, the residual, squaring it, and then dividing by n minus 2. And then taking the square root of that value. So, and it's just this capital S. So we're going to use n minus 2 instead of n minus 1. We'll talk about that more at another time. But this is the equation for standard deviation of least squares regression line. And it's really nothing different than our regular standard deviation, other than we are using predicted values, and we're also using n minus 2 in the denominator. All right, so there's some technology that you need to work through. I just wanted to highlight that. All right, so how well the line fits the data is R squared in regression. And the R squared data is going to be, we call it the coefficient of determination. And by the way, it is the squared value of the correlation coefficient. It's a value which tells us how well the least squares line predicts the value of the response variable y. All right, so we're going to take the 1 minus the sum of the squared residuals divided by the sum of the squared totals. So the residuals would be the difference between the predicted value and the actual value, right? That value that we're going to use for standard deviation. And then in this case, we're going to use the actual value minus the mean value for the sum of the squared totals. All right, so that's just one way to understand how well the least squares line predicts the values of the response variable. And of course, the higher we get to 1, then the better that the least squares line predicts the response variable. Okay, all right, so now let's talk about, this is really interpreting computer regression output. We're going to, so this is predicting the, or using computer output to take a look at where the values are for the least squares regression line. So 3.505 is this constant value on our coefficient. That's your y-intercept. This is your slope, negative 0.00344415. I have r squared at 60.6. There's adjusted r squared, which we can talk about later. And then there's a standard deviation of the residuals. All right, so this line does an okay job. There is some relationship of accurately predicting the weight gain based on the amount of NEA calories burned. All right, so this is just a computer printout. All right, so we're nearing the end. So we need to talk about correlation and regression. So there's a distinction between explanatory and response variables is important in regression, but not in correlation, because regression minimizes the y residual only. In correlation, it doesn't matter which one is x and which one is y. The correlation will give you that relationship regardless of which one is the response or explanatory variable. But because regression is minimizing the response variable, it matters which one is identified as which. So correlation and regression lines describe only linear relationships, so please keep that in mind. Correlation and regression lines are not resistant to outliers or large deviations, so that's going to affect, of course, the mean values. We saw that when we compared mean and median. And then, of course, correlation and association does not imply causation, and we recall that discussion from a previous chapter. All right, that's it. Thanks for joining us. This was a little bit on the long side. I hope you learned something about least squares regression. That brings us to the end of this chapter.